So today, we're diving into one of the most clever tricks in the entire AI playbook: semi-supervised learning. It's all about how an AI can get incredibly smart without needing a person to hold its hand and feed it every single piece of information. And to really get our heads around it, let's start with a simple story. I want you to picture 3 different students. You've got the one who has a teacher for every single question. Then you've got the total opposite, the lonely genius who has to figure it all out by themselves. But the third one, that's our star for today. This is the resourceful student, the one who gets a few key lessons and then is handed a mountain of homework to master the subject on their own.
Okay, so let's properly introduce these 3 students, because honestly, their study habits are a perfect mirror for the 3 big ways we approach machine learning today.
On one end of the spectrum, you have supervised learning. This is our student with the complete answer key for every problem. Super effective, sure, but it's a ton of work for the teacher to create all that material. Then, on the other extreme, you have unsupervised learning. This student is basically thrown into a library with no instructions and told to find interesting patterns. It's ambitious, you gotta give them that, but it's really hard to guide.
And that brings us right to the hero of our story, Semi-Supervised Learning, or SSL for short. This is our third student. They get a small, perfect set of notes from the teacher. That's our precious labeled data. Then, they're given a huge stack of practice problems with 0 answers. That's the unlabeled data. SSL is the magic of using those few perfect notes to intelligently work through that entire mountain of practice problems.
So, why is this third student approach such a game changer? Well, it's because it's built perfectly for the kind of data we actually have in the real world.
Here's the fundamental problem we face. Labeled data, the stuff that's been carefully sorted and checked by human experts, is wildly expensive and super hard to get. Meanwhile, unlabeled data, just raw images, raw text, raw audio from the internet, it's everywhere. It's abundant, and it's basically free. Semi-supervised learning is designed to perfectly bridge this exact gap. It uses that tiny sliver of perfect data to make sense of the massive, messy pie. Okay, so how does our clever student actually pull this off? Well, let's look at the first strategy, which is called self-training. You can think of this as the student using what little they know to make some educated guesses and then learning from their own best answers. The process here is actually pretty simple, but it's incredibly powerful. First, the AI model studies those initial teacher's notes, the labeled data. Then it turns to that giant pile of homework and starts predicting the answers. Now here's the really clever part. The model doesn't trust all its answers. It only takes its most confident predictions, the ones it's, say, 99% sure about, and adds them to its notes as if they were true. We call these pseudo-labels. Then it just retrains itself on this slightly bigger set of notes, and it repeats the process, getting a little bit smarter each and every time. But you knew there had to be a catch, right? The big risk here is something called error amplification. If the model makes a confident mistake early on, it then teaches itself that mistake. It bakes the error right into its own study material, reinforcing it over and over again. The student literally teaches themselves the wrong lesson and gets more confident about it each time. Not good.
So, how do you fix that problem? Well, you get a study buddy. Our next strategy is called co-training, and it's all about the power of teamwork and getting a much-needed second opinion.
With co-training, you have 2 AIs, 2 students, working together. But here's the trick. They're forced to study the material from different angles. It's like one student reads the textbook, while the other only looks at the professor's lecture slides. They both make their own predictions on the homework, but then, instead of grading their own work, they teach each other. The first student's most confident answers become new study material for the second student, and vice versa. It's this back and forth, this constant cross-checking that helps prevent either one from going too far down the wrong path. Now, this might sound a bit abstract, so let's use a perfect real-world example. Classifying a web page. To figure out what a web page is about, you could have one AI model, one student, read all the actual text on the page itself. But the second model could look at something completely different, the words used in all the other websites that link to that page. These are 2 separate, independent views of the same problem, and when you combine them, you get a much more accurate result. Okay, so self-training and co-training are all about making better individual guesses. But our next 2 strategies are a little different.
They zoom out. They're all about understanding the bigger picture, the overall shape and structure of all the data.
First up, we have graph-based methods. With this approach, our student creates a giant mind map, connecting every single data point, both the labeled notes and the unlabeled homework. And the core idea is really intuitive. Things that are similar should be closely linked together in the map.
This whole process is called label propagation, and here is the absolute best way to picture it. Imagine your data is a big, dry sponge. Your few labeled data points are like single drops of colored ink. When you drop that ink onto the sponge, what happens? The color, the label, naturally spreads outwards, seeping into all the nearby connected parts of the sponge. A single cat label can slowly color all the unlabeled cat pictures it's connected to.
Okay, so that was one approach. Now here's a totally different philosophy. It's called Low Density Seperation. This student has a very different belief. They believe that the best way to draw a line separating two different things, say pictures of cats from pictures of dogs, isn't to cut through the middle of a group. No, the best place for a boundary is in the empty space between the groups.
And this is why all that unlabeled homework is so important. It shows the model where the crowds of data are. Without it, an algorithm might just slice a line anywhere. But with it, the model is pushed to find a boundary in a low-density region, the empty space, the gap between the crowds.
So let's put these two side by side, because it really makes the difference pop. Graph-based methods are all about the global structure, how labels spread through a whole network based on similarity. Low-density separation, on the other hand, is laser-focused on one thing, finding the single best place to draw a line, making sure it passes through the emptiest territory. They both use the unlabeled data to see the big picture, just in very different ways.
So, we've gone through all these really clever study techniques, but let's bring it back to the real world. What does all this actually mean? How does this lead to a smarter AI and, well, a smarter world?
Well, this is where SSL really shines, especially in fields where getting that labeled data is a massive pain. Think about speech analysis. You need a human to literally sit there and transcribe hours and hours of audio. It's a huge bottleneck. Or what about analyzing massive DNA strands for protein classification? Or in medicine, where you need an expert radiologist to analyze every single scan? In all of these areas, SSL lets us take a little bit of that expert work and apply it to vast oceans of data, making everything more powerful and accessible.
So, let's wrap this all up with a quick look at the pros and cons. Self-training is the simplest, but you run that risk of it teaching itself the wrong thing. Co-training is more robust, but you have to be able to find two good, different ways to look at your data. And the graph-based and low-density methods are really powerful at finding structure, but they can be more complex to get right. In the end, there's no single best method. It's about picking the right study technique for the right exam.
And that really leaves us with one big, fascinating question. At its heart, semi-supervised learning is about making AI more independent and more resourceful. As these techniques get better and better, AI is going to learn more from the vast, unlabeled world around us with just a tiny bit of human guidance. So the question we're left with is, what's the next great problem that this more independent AI is going to solve?